Ladies and gentlemen, I would like to welcome you to our event, 24/7 Heat and Electricity Powered by the Sun. It is an official side event of the Berlin Energy Transition Dialogue and organized of 3 associations, and I like to welcome you on behalf of the German Solar Association and the German Association for Concentrated Solar Power and the German Energy Storage Systems Association. And my name is Juliane Hinch. I represent the Concentrated Solar Power branch, and this, together with my colleague Jan Knack, I will lead you through the program tonight. The Storage Association is represented by Valeska Gotke today. And yeah, we will have 2 sessions today, and the first one will be on solar process heat for industries and thermal storage, and the second is on CSP PV hybrid systems with thermal storage. We have a full agenda packed with keynotes, technology, and project presentations. You can use, as soon as we fix it, the chat function to post your questions and make remarks, and we will pick up all the issues or few of the issues later on in the discussions at the end of each session. We will record this event together with all the presentations of the speakers. We will afterwards. Now, I will limit my talking to maximize the time for all the speakers, and timekeeping is in this virtual format is absolutely essential, so I kindly ask all the speakers to stick to the time limits. And yeah, with that, we will start with session 1. Jan, go ahead.
Thank you very much, Juliane. Hello from my side as well. My name is Jan Knack. I work for the German Solar Association, and I'm very happy to continue with this tradition which we have done in previous Berlin Energy Transition Dialogues. We have a very full program. We will have 2 sessions, 2 very interesting keynotes, and 13 companies presenting themselves. So I'm not going to want to waste your time. I'm very happy to introduce our first speaker. Our first speaker is Mr. Michael Taylor. He is Renewable Costing Analyst of the International Renewable Energy Agency. Michael, he has been senior analyst and has more than with IRENA for quite some time, and he has more than 25 years of experience in energy modeling. And he has done all kinds of very interesting studies, and I think what he's going to show us now is very up to the point, very new knowledge, and it should be very interesting for all of those of you who are interested in the CSP and solar thermal heat sector. And I'm right now handing over to Michael. I hope, Michael, that you can click through your presentation if you're using your keyboard.
Let's see. We'll give it a try.
I see that you are. Okay.
Looks good.
Oh, wonderful. Okay, thank you very much, Jan, for that introduction. It's a pleasure to be with you here today, virtually, of course. Good morning or good afternoon to all of you around the world. What I want to do is give you a very quick overview of some of the work we've done around the costs and performance of not only concentrating solar power, but some very exciting work we're doing on solar thermal for industrial heat and process heat. Okay, it's not working super well. Okay. Right, so what I'm going to present to you is some historical background on the concentrating solar power costs, and we release every year a report on the evolution of the costs and performance of renewable power generation technologies. Last year, over half of all new capacity deployed was cheaper than the lowest cost coal-fired option for new capacity. So the world has changed dramatically in the 8 years that I've been at IRENA. And what we've seen is that costs are not only falling, but they're absolutely at low levels as well. So we're not just competing on the basis of for new capacity, but increasingly undercutting even the operating costs of existing fossil fuel-fired power generation. Okay, very hit and miss. For advancing my slides. Okay, and that's even cut off the bottom. So what we've seen is that the technology cost reductions are coming from technology improvements, more competitive supply chains, economies of scale in terms of the overall market, and also in terms of developer experience as well. So what we've tried to do, I used to be an energy modeler, and it's a challenge finding robust, easily understandable assumptions. So what we try to do is be as transparent as possible with the data. So what we've done is collected real world project cost data, and we have about 18,000 projects in our database now. We complement that with a PPA and auction database. In the project cost database, we have total install cost, capacity factor at the project level, and some assumptions for O&M and cost of capital. All that information is hidden in the PPA and auction database, but with the price of these tenders, we do get some interesting information. So what has been the recent cost evolution between 2010 and 2019 for newly commissioned projects? This is a little bit complicated, this graph. I'll take you through it because you'll see more of these bubble graphs. Each circle is a individual project. The center of that circle is the levelized cost of electricity on the y-axis. The diameter of that circle is the size of the project to give you an idea of the scale. The bold lines you see there are the global weighted average for each year, for each technology. So on the right-hand side, you can see the declines. At the same time, we have the 5th and 95th percentiles for each year for each technology. And finally, the fossil fuel-fired cost band that runs directly across the bottom of this chart. So you can see, don't forget about the mature renewables. They're obviously low cost, dispatchable, help us integrate variable renewables. But solar PV cost fell by 82%. The levelized cost of electricity between 2010 and 2019. CSP has come down dramatically as well, but is still, at least in levelized cost terms, or was rather in 29, relatively expensive. The wind technology is often now very competitive where you have onshore wind. I just want to focus on the idea here that for the solar and wind technologies, what we've seen is really dramatic cost reductions. And I'm giving you, jumping ahead a little bit here, because the 2010 to 2019 values are these levelized cost of electricity. But on the right-hand side, you can see what the PPA and auction results tell us for the out to 2021 and 23. And so if we click on, hopefully, okay. Okay, Jan, can you click, please? Okay. All right, so diving into, so this is a chart of the concentrating solar power costs evolution. So the levelized cost of electricity, we assume quite a conservative weighted average cost of capital of 7.5% in the OECD and 10% elsewhere. And so up to 2019, we have the project data, and you can see it declining through time to the top of the fossil fuel cost band. But with the auction and PPA data that we have for 2020 and 21, we can see this more step change and the costs coming down into the range of around, say, 7.5 to 10 cents per kilowatt hour on average. And this is really important for the energy transition because we see a bright future for CSP, given it can be a low-cost, dispatchable technology because of the low-cost thermal energy storage that is attached to CSP. Okay, Jan, can you click forward one? Okay, great. So what's going on? What are the trends that are driving this cost reduction, despite the fact we're only at around 6 gigawatts of deployment? First of all, it's a shift to CSP in higher resource areas, higher solar resource area. Jan, can you click? Okay, we've got a broader range of experienced developers who've developed projects. We've got more competitive supply chains, although they could be a lot more competitive. And we've got the technology improvements that are coming through. Not to forget the importance of competitive procurement, which is really driving cost discovery. And we've seen low cost of capital in many cases. So let's talk about a few of these drivers. So here we have a chart that looks at the evolution of the capacity factor of newly installed CSP plants. And you can see on the left-hand side that as we move through time, we've had a couple of things happening. We've shifted to projects with greater duration of storage. And then if we shift to the right-hand side, at the same time, these projects with greater storage in recent years have often been located in areas with greater solar resource. And you know, I talked a little bit about how we think CSP is a very important technology for the energy transition, particularly for the integration of variable renewables through time. And so we've looked at the cost reduction potential as well going forward. We've done this in conjunction with DLR, who have a fantastic set of experts in this area and great modeling capabilities. And we've basically gone through a process of developing a reference plant, identifying cost differentials and local cost components to look at where the technology could be with the existing, with a significant increase in deployment that we need to meet the Paris Agreement objectives. And we see a continued potential for cost reduction for the technology of around 30 to 35% in terms of total technology costs, installed costs. The way in which that is unlocked varies a little bit between parabolic trough and solar tower, but we don't have time to go into that in great detail, unfortunately. And what this means is if we look at the G20 countries with good D&I, by 2030, with this conservative cost of capital assumption that I mentioned of 7.5 and 10%, we can get to some very attractive cost of electricity for what is a dispatchable 24/7 technology. And we've done extra work with other organizations to try and promote this outlook for CSP, and we released in February a report with the World Bank on this, on the market. So if we can get this growth and scale that is not there now, unfortunately, given the support is relatively weak, you know, we see a very strong potential for cost reduction and a very important role for CSP in the Sun Belt and integrating very high shares of variable renewables. But you know, CSP has a little bit of a challenge in terms of it is considered, you know, slightly higher cost. It doesn't take into account the value of CSP, and we make that point in the report with the World Bank. But if you start to think about CSP in terms of firm dispatchable renewable energy, it really is all out on its own. So this chart shows levelized PPA results for solar PV plus storage and the duration of storage on the x-axis. And you can see a cluster between 0 and 4 hours of storage, where you've got very competitive solar PV. But like I said, CSP with, you know, the DEWA project in the United Arab Emirates is really all out on its own, and you have to remember again the difference in deployment between CSP at 6 gigawatts and PV at a lot higher. So does concentrating solar power have a cost problem? Perhaps only if it isn't valued for the services it provides. We're very happy to be doing more work on the end-use sectors, and solar thermal heat we think can play an important part of that. If we're going to meet net zero, we have to do the end-use sectors sooner rather than later. And we've been working with Solrico and Solar Payback to help fill in what is a really quite significant gap in the terms of verifiable cost and performance data for solar thermal heat, notably for industrial processes. And we think this is, you know, an important process that will aid policymakers in properly considering solar thermal in the energy transition. We're trying to do as we do for power gen, so collect project-specific costs and performance data, and end up with a representative database which we can talk about with policymakers and integrate into our models at IRENA, but also researchers can use as well. We're balancing, as always, the difference between the depth of detail that we ask for and the rate of response. So we're trying to get just enough detail to understand the dynamics around costs in different markets for different solar thermal technologies, but it is a bit of a trade-off. We're very pleased with the engagement we've had from all the suppliers that's been approached by Barbel and her team. We're up to around 752 data points for large-scale systems globally that represents 786 megawatts of capacity. I don't want to take up too much time talking about the database itself, but there are, you know, clearly additional markets and technologies that we'd like to flesh out to have more representative data, and I'll talk about a little bit about that in a minute. Overall, the database is dominated by district heating projects because of the sheer scale compared to the other applications and the relative maturity of the market. So we have some very preliminary results here that I'd like to share you. We're in the process of finalizing this database and hoping to publish either before the summer or just after summer. And you can see here for Austria and Germany, the total system costs, and we've put this into a per kilowatt hour, and I know that the industry is more attuned to thinking in meters squared, so there is also euros per meter squared on this chart. And you can see the evolution for Austria and Germany for the projects that we've been able to collect. So there's been quite a significant cost reduction. So if you remember back to the chart which I showed, the cost reduction, say for offshore wind or onshore wind, these are actually really, you know, quite comparable cost reductions for very small markets, actually. There's been some impact from economies of scale. As you can see, there's some larger dots here, and underneath I've put the actual average project size in the database for each of those years. So it's more pronounced, say, in Germany than in Austria with their smaller systems. So yeah, these results are actually, I mean, were personally a little surprising, but very encouraging considering these are markets that are actually not growing dramatically. If anything, they're shrinking. So very encouraging and tells us a little bit about what might happen if we had more support. Looking at solar heat specifically for industrial processes, and in Europe where we can, if you like, more or less assume that we're making comparable decisions around boundary conditions and cost structures. Again, costs have come down. There's again evident impact of economies of scale. There's not a lot of projects, but this is the data we do have. and it excludes the 10 megawatt French project, which we believe is being commissioned this year. So if we added that in, the cost reduction wouldn't be 43%, you know, it would be somewhat higher actually. So translating that into a levelized cost of heat with some basic assumptions about a 25-year life and 1% O&M of CapEx, we get to a weighted average cost of capital real in 5%, which in some cases may actually be quite high for some of these projects. We see a larger reduction in the levelized cost of heat from these projects because the share of the projects we have shifts to areas with a better solar resource, so the yields are somewhat higher. So even more significant reduction in the levelized cost of heat for these projects, although still somewhat high, around US 76 per megawatt hour. Mexico, we've had really good response from suppliers sharing data for commercial and industrial projects there, and we have good data to 2018, where we see a quite significant reduction in not only the install cost, but, and again, a larger decrease in levelized cost of heat. And obviously here, this is not so much due to projects with better resource, but better systems with greater yields. Unfortunately, the data for 2019 and 2020 is very thin and not really representative. So I'd caution, you know, that jump is probably not representative, and we're hoping to get additional data to actually flesh out those 2019 and 2020 values. Finally, just focusing in on concentrating ship projects. We have a much smaller database here, so it's only around 52 projects and 12 megawatts. If we look at the installed cost per kilowatt between process heat liquid and process heat steam, which is the first chart here, left and right hand sides, overall, the costs that we have are about the same. But if we look at the levelized cost of heat on the right-hand side, you see there's quite a difference, obviously, because of the challenges, not the challenges, the additional costs that arise in those projects. So very encouraging data, very good collaboration with Solrico and Solar Payback. In fact, I'd have to say it's the gold standard as far as IRENA is concerned. We're having a great collaboration and really interesting data that's coming out of it. And we hope to round that out in the coming months, perhaps with your support. Thank you very much for your attention.
Thank you very much, Michael. This is very, positive to see that on the CSP side, as well as on the solar cell process side, we are reducing the costs considerably over the last year. This is very promising, and of course, we hope to see more and more projects going online in the next years to find out to bring down how we can bring down the costs even further. We will now go over to see some of these projects, and we will then start with the projects, with different projects. We have the next presentation. It is by Yuvaraj Pandian of the company Solarlite, and it's on solar process heat. And I'm going to hand over the panel to you, Yuvaraj. You can now click forward the presentation, and you have 5 minutes to tell us, what kind of project this is about. The floor is yours.
Thank you, Mr. Knack, for the organizing, and a very good afternoon, or good morning, good evening to people from different time zones. So my name is Yuvaraj Pandian from the company Solarlite. I'm the solar analyst here. We are going to see a bit about solar process heat in general, various application possibilities, and what we or any technology provider can offer for process heat applications, like for industries, utilities, and so on. Okay. So a brief background. So Solarlite has been in this business for nearly 20 years. We introduce ourselves as EPC for parabolic trough collectors. Parabolic trough is our core component. This is the only product that we offer in different dimensions, designed to operate with different fluids, etc. Our key innovations are direct steam generation. And on the right-hand top, you can see a sky view of our parabolic trough power plant in Thailand, 5 megawatt capacity. It's the world's first commercial DSG plant. And we have also been, developing projects. It's not yet in construction, it's in planning phase to operate with molten salt up to 550 degrees C. And I think the rest of the information, pretty much everyone knows it. CO2-free modular design applies for all concentrating systems. And of course, research is a key integral topic in our company. At any given time, we have 2 or 3 R&D projects running together with the key players in this field, like the German Aerospace Center or the CMAT at PSA, etc. Okay, next. So we don't have to talk about power. We are concentrating on process heat. We have been offering and continue to offer heat steam solutions up to 400 degrees C in the range between 1 to 100 megawatt thermal. And some of the key energy dense industries are mentioned here: the breweries, food and beverage, chemical, paper, pulp, etc. The key issue is integrating with existing boilers, fossil fuel boilers, gas, biomass, coal. And that is the trick to have a smooth operation between 2 heat sources. Yeah, this is our key know-how. And naturally, desalination, thermal desalination using MED, MSF for sea or brackish waters in capacities anywhere from 100 to 200,000 cubic meter per day. And cooling, district cooling for communities or large commercial cooling systems for 200 to 100,000 RT systems. And finally, most of you are not aware of or just heard about it, is the enhanced oil recovery for the heavy oil fields, mostly in the Arab countries, the Californian desert, etc. And we are collaborating with key players like Chevron and so on to supply solar steam that works in tandem with the existing gas ODSGs. So this is in general. Okay, how do I go next? Yeah, thank you. So just as an example, 2 of our projects, and I have to take both of the projects from Belgium just to show the audience we don't necessarily have to build concentrating solar plants in the desert. We also have to bring it to where people live, where people can use it, and this is more a proof of concept to show it's working even in low radiation regions like in Belgium. Belgium has, in comparison, even worse radiation than in Germany. So there we have 2 plants operating since last year. They are each in capacity comparable, roughly 500 kilowatt thermal, using Helisol as HTF, generating steam in a secondary circuit. And one interesting thing you see on the left-hand side image, they are elevated by 6 meters to allow a cargo train to go beneath it. Yeah, this is just to show the port of Antwerp. It's possible to use a lot of space that is available there, a lot of hectares, that they can make use of it and generate solar heat for their energy demands. And Port of Antwerp being the biggest heat consumer in Belgium. And okay, this is a bit tricky. It basically shows the measurement from these Belgian plants. Yeah, on the left-hand side, all these circular dots you see for the third quarter last year, July, August, September, and they shows what is the expected heat generated for a certain DNI. And you see the measured, it's in continuously, or more than 90%, it's above the expected value. So the plants are performing better than we expected, considering the safety factors and so on. Yeah, and even interesting, you can see the blue line here in the graph on the right hand side. Yeah, this shows the temperature. This data is from 4 weeks ago. The temperature is continuously below zero, or mostly between -5 and 0. And you see with the low radiation we have, the plant is working perfectly without any interruption. So the key point here is low DNI is not a big issue for the performance technically, yeah, and low temperatures doesn't matter as long as we design the system appropriately. By the end of the day, it's a matter of economics, and every case is different. And some other key points from these projects. So reliable interaction with the existing heat generators. So we have not got any complaint from the client saying, hey, your steam generation system is bothering mine. I need to shut it down, or I have to shut yours down. No issues so far. It's going smooth. They are completely automated systems, no people present there, and we only go there for scheduled maintenances twice or thrice a year. Yeah, and most interesting thing is the mirror cleaning in these regions. For these mirrors have been far lesser washing cycles than we planned. One plant we cleaned only once in the last 14 months, and the other plant we haven't cleaned at all. And we have not seen any significant performance reduction so far. And finally, so utilities, we are in preparation at the moment to offer solar heat to high temperature city works. They're called the Stadtwerke. In Austria, Germany, everywhere. Yeah, they usually operate up to 140, 150. And we are at the moment in preparation of 3-4 projects in the range of 4 to 14 megawatt thermal to apply solar heat, pressurized hot water to these networks to show we can pretty much integrate into any application and do our best. That's it. Thanks for your time. And if I have taken more than 5 minutes, excuse me, I still need to refine myself. Thank you.
Yeah, thank you very much for this very interesting presentation. I would like to also ask the listeners to this session to ask your questions via the chat to all presenters and organizers. I hope you see that function as well. Yes, as two single presenters. We are proceeding basic with the next speaker, which is Mr. Scheuerer from Protarget. I will hand over the mouse to you. One moment. Okay, and I hope everything works out now. The floor is yours.
All right. So also hello from my side to everybody. My name is Martin. Does it work?
Shutting.
Jan?
Okay. Oops. Is
Okay.
das shutting down? Was ist das Internet down oder was? Oops.
Geh du mal
Jan,
rein.
your microphone is on. Let's start again. So, yes, hello everybody. My name is Martin Scheuerer. I'm the director of Protarget AG. Our company is specialized in solar thermal systems, and today I want to talk about how our technology can supply the food industry with process heat and steam. Jan, thank you. So a few words about Protarget AG. Our company was founded in 2009, being specialized on solar thermal systems for industrial process heat and steam generation. Today we are offering mainly two solar thermal technology. One are vacuum tube collectors, so-called CPC collectors, to provide hot water up to 100 degrees to industrial processes. Second technology is CST, using the parabolic trough collectors to provide process heat and steam of up to 420 degrees. I will show you now an example where we have basically used both technology to provide a food producer with steam and hot water, and show you a bit more about on which levels these technologies can be integrated. So what you see here is the company Kern. It's an orange juice producer or fruit juice producer in Cyprus. Very easy to spot also when you fly into Cyprus, because all the roofs are oranges. So here you see two solar thermal technologies in the background, the CPC collectors mounted on the roof, providing hot water at 95 degrees. And in the foreground, you see a parabolic trough system providing steam at about 190, 195 degrees. This system is also equipped with two storages for either of the system to be able to dispatch energy 24/7. I will go now a bit more into the details of the system. You see a top view of the company. In the bottom part, close to the steam boiler house, the CPC system, as I said, mounted on the roof, providing hot water at 95 degrees. This water is used to preheat the feed water of the conventional boiler. The system is also equipped with a thermal client storage in order to provide this thermal energy also in the night, in particular over the weekends. On the top, you see the parabolic trough solar field, which is heating thermal oil to 420 degrees, which then is converted in a steam drum to 190 degree hot steam that is used directly in the production line, in the pasteurization and package line of the company. This system is also equipped with a storage, a so-called CTES storage, which uses concrete, storing the energy at a very high temperature level, also be able to provide thermal energy 24/7. With those two storages being in place, we are able to run the company on solar. And the working pattern of this company is 4 a.m. to 2 p.m. This means when the people start working at 4 o'clock in the morning, their systems are already hot from the sun. Next slide. How is it integrated? So basically, we have 2 ways of integrating a solar thermal system. We can do this either on the system level, which in our case is done with a CPC system, or we can do this on the process level, which we do with a parabolic trough system. So this means the parabolic trough system is feeding directly into the production process or in the packing line. The CPC system on the system level, but which is then also contributing to the steam by preheating the boiler water. I have a short movie for you to show you how this all looks in reality. So you see the roof installed CPC system.
Okay, we have to come to an end.
And now the internet died.
Not for us, but we have to come to an end.
So we would can you try to start it, Jan?
Yeah, I'm trying to start to start it.
Okay, on the left side, you see the existing fuel boiler, nasty, dirty piece, which you find in most of the industries still working. And right next to it is the parabolic trough plant feeding directly on the process level into the production process of the fruit juice company.
Okay, thank you very much. I had to cut this a bit short. Can you hear us?
No problem.
Okay, good, because we had a major technical issue in the beginning of the presentation. Yes, thank you very much. Here are the contact details, and we're going over to our next presentation. I would say, oops, so, one moment. Okay. Yeah, the context. Okay. Next presentation, we also try to stick to around 5 minutes, is Paula Alfonso of Industrial Solar or Clean Energy, Clean Industry Solutions, and I'm going to hand over the presentation to you. One moment, Paula. Yes, I hand it over to you.
Yeah, you can hear me?
Go ahead. Yeah.
Yeah.
Yes.
I don't think it's working.
For the participants, it should work because I also have a participant's screen.
Yeah, but I cannot.
The mouse? No?
No, I don't get the button of the allowed.
I can click forward if you want. Can you see the screen?
Okay, yeah, I see it. I have said you, and you can do it. We do it faster that way. Yeah. So well, thank you. My name is Paula Alfonso, and I'd like to present you some solutions for sustainable industry that we have. So, as you may already know, 50% nowadays of all emissions are caused by burning of fossil fuels. And if you can go to the next slide, you will see that that. Next slide, please. Jan, can you? Hi. Yeah, next one. No, sorry. Mine is going too fast. Anyway, you can see the slide afterwards. I will do it fast. 30% is due to industry, and in the most of cases, industry demands heat and electricity, and this demand is always supplied by fossil fuels. 1/3 of the demand is due to heat, and the other part is due to electricity. 3 times more heat is demand as electricity. That was what that slide said. And as we look for is to supply some solutions where we can use the solar energy that you may see here is everywhere, it's abundant, it's clean, and so on. Next slide, please. So if you may see that not everything is heat, also we have some most of the industries that require heat also require water. So that's why our industry, so our company, next slide, please, Clean Solution Holding holds 2 subsidiaries, what is Industrial Solar and Solar Spring. So Solar Spring is an international pioneer in the field of membrane distillation, offering innovative waste and drinking water treatment technology. You may go to the next slide. And then Industrial Solar is where our work is international leading technology solution provider, and we offer sustainable turnkey solutions for customers in several industries. Jan, can you change the slide? Or, so here you see the holding, that is Clean Industry Solution, and the 2 companies I already mentioned. If you go to the next slide, I would like to present you an example of our Fresnel collector. That is one of our solutions. So this is a Fresnel collector installation in Jordan for the tobacco industry. It's around so more than 1,000 square meter collector area installed in the roof of the facilities of our client, and the collector supplies steam to the client process, and also supplies steam to absorption chiller that is used to cool off also the facilities and the process. The collector itself, as I said, is installed on the roof area of the client and direct connected to the client system, and provide around 700 kilowatts thermal power. If you go to the next slide, you may see a little about our Fresnel technology. We do some models, and these models can be installed in serial parallel. Each module consists of a set of primary mirrors and an absorber tube. The primary mirror will concentrate the sunlight onto the absorber tube, and there is a secondary mirror above the absorber tube that increases the efficiency of the system. And well, also went faster, but the system can be integrated in several parts of the process. And as you can see here, we provide several solutions, not only like the Fresnel collector, but another, we don't want to give you only a product, but we would like to give a solution. That's why we offer a set of portfolio. And I stick to the 5 minutes, I think, and you go to the last slide. Thank you very much.
Yeah, thank you very much to you as well for keeping close to the time. And we are heading over to our next presenter. Okay, this is still 2 slides. We're going to go to the company Enersolve. who will show us an interesting application for the gas sector. And yes, this works, and I'm going to hand the presentation, the mouse, over to Johan. One moment. Shouldn't. Where is Johan? Yeah. Okay, Johan, please go ahead.
Yes, hello everybody. I'm Johan Louvet from the University of Kassel, and on behalf of NSOL, I'm going to present you. Next slide. A nice application for solar thermal within the solar thermal and renewable heat in general within the gas sector. Next slide. And so here you see a map of, yeah, you can pass, a map of the transmission grid on the left side in Germany with of the gas network with a pressure above 20 bar. And if we make a zoom here around the region Kassel, you see the regional grid, and all the dots that you see on this map are so-called gas pressure regulating and metering stations. And it's the interface between the different pressure levels in the network. And it's similar to transformer station in the electric grid. In Germany, we have above 5,000 of this station all over the territory, and with the heat demand, which is about 1 terawatt hour a year. And what's very interesting is that the temperature range for the heat supply for these stations is around 30 to 80 degrees. And so it's very interesting for integrating solar or renewable technologies. Next slide. Yes, thanks. So here you see on the left side, you have the gas which is coming from the transmission grid at a high pressure, and the gas is filtered and is throttled. And at the output of the throttling, you've got a lower pressure, and if you don't do anything, then you will get here a negative temperature, or in this case it was minus 20, I think. So what is done to avoid that is to preheat the gas with this here, this gas, water gas heat exchanger, and like, let's say, state-of-the-art system, this is done with gas boilers. And yeah, approximately 2.2% of the energy which is flowing here in the form of gas will be used to preheat the gas. And for large station, you can have up to several gigawatt hour per year of heat demand. So here you see a typical heat demand profile of a station, and you have a strong seasonality. And here with a ratio 1 to 5 between summer and winter. Of course, this varies depending on the station. And next slide. If you want to integrate solar heat, then you would design your collector field in order to cover the demand in the summer. And yeah, of course, depending on the heat demand profile, you can cover between 15 or 30% of the total demand with solar. So here are a few examples of a system which were already implemented here in the region of Kassel for a local gas net operator, AIN Nets. And you see, you don't only have solar thermal, but you also have some other renewable technology which were integrated in the systems. Here you had district heat connected to a local CHP biogas plant. And in these two cases here, you also had a gas-driven heat pump connected to the system. And what's also interesting is that these plants are operated, or two of them are operated in contracting. So the heat is sold by the plant operator to the gas net network operator.
Could you come to
here? Yes, here an overview of the process heat in Germany until the end of 2018, and according to the sector. And you can see that gas pressure regulating stations are already making an interesting share of it, about 10%. And if you go to the last slide. Yes, so here, if you are interested in the application, of course, there are still a lot of potential. You can contact us, and you can also have a look, if you want, at a quick pre-feasibility assessment tool that we've developed in the framework of a research project. And here it's possible to make a quick first assessment for projects. And with that, I thank you for your attention.
Okay, thank you very much. We hear Dirk Bittner of Axiotherm on PCM systems. Please, and Dirk, I'm trying to hand over the mouse to you. Yeah, one moment. See if it works. Yeah. Okay, now the floor is yours.
Yes, okay. Thank you very much, and thank you for this great opportunity to present you our power to heat and power to cold technology to solve one of the main problems of this energy transition. It's namely the highly efficient thermal storage problem in the low temperature range. So I hope, does not work. Oh yes, but how to realize? Okay, now I'm one step further. I just want to show you briefly our basic technology. It's very easy. If you cool down, for example, water from 20 up down to -10°C, you go through the transition point where you create ice, water ice. Oh, now it's running. Oh, one moment. So in this case, if you make a phase change, and the water is in this moment a phase change material. So it's very nice to have a phase change material like ice with 0°C, but this is not usable for many applications because it's sometimes too warm or too cold. So it's necessary to have, one moment, it does not go on. Why? Can you maybe make a click? Ah, yes. Thank you. Okay, let's go on this way. So you need some other PCMs, phase change materials with different temperatures, higher temperatures, lower temperatures. Everything is do we have. And what is the big benefit? We have the highest energy density at this heat transition point. So in this moment, we have the smallest temperature difference and can realize highly efficient storage systems with up to 5 times higher storage capacities at same space, like for example, sensible systems. Oh yes, oh, now I can see. The technical application, very easy. Just take something like a vessel, put in our macro-encapsulated phase change materials, let flow water through, and we have the ready for work phase change material storage system. So the first project I like to show you is a PV to heat project in Denmark, together with a Thansram company. We have there 23 houses, and each of them has a heat pump, a PV system, and a PCM storage system. They are all connected by a web cloud system management, and we have the feasibility for the weather and electricity prices. We realized by this maximum of PV self-consumption and have, of course, minimum electricity costs. One main point is that we increase the heat pump efficiency up to more than 42%. This is a fantastic value. You can't reach this with a technical modification. We also, also have realized this technology there as district heating, so you can see there are a lot of chances. The next project I'd like to show you is PV to cold. Cooling energy is very important for the future because we will have a lot of demand for cooling rooms, and cooling energy is around 5 to 6 times more expensive than heat energy. In this case, you can see a 50,000 liter storage system in the Futurium. It's in the center of Berlin, near close to the Bundeskanzleramt. And we have there 5 tanks, each with 10,000 liters, and optimizing the technical building systems. We use a peak load reduction, for example, for events where you have where you need a lot of power, cooling power, by peak cutting shifting. What is peak cutting shifting? Very easy. You see the red line there, and this is the highest power of the chilling machine. If you have, for example, an event and you need much more power, the peaks, what do? We just cancel. Or we cut the peaks away. We store this energy before in the storage systems, the PCM storage systems at 12 degrees Celsius in this case. And then we have the option, if we need much more power, we start to deload the storage systems and have enough power to cool the whole building. By this, we have a maximum self-consumption of the PV system. Because each watt hour or each watt we produce go direct into the cooling storage. And we have a maximum COP, of course, through load shifting, and the PCM with 12 degrees Celsius. It's near close to the chilling machine. It's an absorption machine with around 6 degrees Celsius, and the small temperature difference is a major size. And we have a significantly smaller chiller. That's very important. It's an economically thing. So you can see another picture on the right side. And now I'm ready. Thank you very much.
Thank you very much, Dirk, for this interesting overview of the projects you realize. We are going to our next presenter, which is Martin Schichtel of Kraftblock, and let's.
Thank you very much. My name is Martin Schichtel. I'm the CEO of Kraftblock, a young company entering the market of energy storage. And today we already heard a lot about high temperature applications and high temperature storage. If we speak about high temperature, really mean 350 to 1300 degrees C of storage range. So we are aiming in one point to industrial applications like waste heat recovery applications, but on the other hand also to the CSP, especially to new developments. On this slide you can see how we try to position our storage system. It consists mostly of a newly developed storage material, a sensible type, which uses 85% of recycled materials, and then it's put into container systems like ISO containers, 10, 20 or 40-foot containers, just to do a couple of things. One is to have mobile applications, and the other one is to stack all those containers together to large-scale utilities. What we mostly do, you can see on the marked green lines, we started with heat-to-heat applications, typical in ceramics and glass industry, but meanwhile we are also building up the first projects from renewable sources to the heat applications itself. If you speak about just industrial waste heat, there's a lot of waste heat available in steel and metal forming industry, glass and ceramic industry. It should be recycled, and it is recycled partially, and it will be recycled a little bit more. I will not show now the pilots in those industries, but one application we really like and our customer like, it's a mobile storage system. This is a very small container, 7 cubic meter container with the whole system, and it stores 2 megawatt hours of useful energy at a 480 degrees C level. So very compact, high energy density for a sensible system. In this case, it is charged by a small CHP with electrical output of 2 megawatt on the left side. So we designed a charging system from the CHP to 480 degrees C to our storage. Then it's decoupled and transported to the customer, which usually use this heat as carbon dioxide free heating for the hot water system. From the point of view of renewable energies, we also go our path right now. I don't do anything, so let's skipping through the slides. Let's see if it works now. Okay, So we call it renewable energies in existing technologies. Why? Because we usually try to replace, for example, a conventional fired system against a renewable supported system. This could be CSP, this could also be renewables from renewable electricities from PV or from wind farms. This is quite attractive also to our customers, mostly outside of Germany, because there are also subsidiaries which support those solutions. But that's definitely highly interesting. What we are also looking for, I would like to present a project in this scale, but it's not allowed yet. Will take 3 or 4 weeks, then we will show the results. CSP is also very interesting for us, but not, let's say, the old way of CSP using molten salt as heat transfer media and heat storage system, more the new applications which are using also hot gases as heat transfer media and targeting for temperatures like 1000, 1200, 1300 degrees C, because there our storage system is really the perfect fit to those systems. The interesting thing about our storage system is also that you build the system like an open technology system. It means you can charge it by thermal oil, you could charge it by molten salt, you can also charge it by hot gases. So it's a universal range. It could be charged. Of course, you have to tailor the interfaces, but the internal of the storage always is the same. What we started actually a couple of weeks ago as a joint project together with UPC, DLR, SPF, and a couple of more partners, the advanced thermocline concept for thermal energy storages. At least it means it's a combination, a hybrid system using our solid state material as a cheap filler but highly efficient filler in combination with the molten salt technology in order at least to reduce the costs of those systems. So I think we are very well aware of the opportunities for the future, especially for a CSP. We try to build our storage that it could be used over there, and hopefully it will. Thank you.
Thank you, Martin, for this presentation on the storage technology. Very interesting. And now we come to our last speaker of this session, which is Mr. Reuter, Hannes Reuter of Energy Nest. Okay, the floor is yours.
Okay. Thanks. Good afternoon. Hannes Reuter from Energy Nest. We are currently implementing a project with Eni in Sicily, where we store solar energy and then dispatch it for steam generation. I will briefly go through how the thermal battery works. If I understand how to click on the next slide. Thank you. Oh, one back. Thank you. So the thermal battery is charged, as you see on the upper left side, by a heat source, which can be either electricity, waste heat, or steam, or in the case of the Eni Gela project, by solar thermal. The heat is then transferred by a heat transfer fluid to the thermal battery. This HTF then also dispatches the energy back to a heat sink whenever needed. This can be either steam directly, then process heat, or re-electrification or compressed air, or as we have in the Eni project, a combination of this. The battery system is modular. You see one module here, a 20-foot container. We also have a 40-foot container made of a special Coca-Cola recipe concrete developed with Heidelberg cement, and stores approximately 2 megawatt-hour each module, and then you size just the battery to whatever is needed for the specific application. The applications are quite vast, so we have on the left side industrial applications like the electrification of industry, or just waste heat recovery from steel plants, for example, or ceramics, then to flexibilization of power and heat generation, And you see here on the right-hand side the case of the concentrated with Eni. The moving of the page is not really easy. Okay, so coming to the specific project of Eni, we're actually quite happy with this project because it's sort of a showcase. Eni having also within its decarbonization strategy to be carbon neutral by 2050, converted the crude oil plant into a big biorefinery, and with our thermal battery, we then add to this by further greenifying this facility. The application in this case is quite a small application, so we have 2 modules in this case, but are looking also to have further bigger plants in the pipeline with Eni. And in that sense, also the footprint that you see is quite reduced. In any case, we can stack the modules up to 6 on top of each other, so the footprint we need is limited. The scope we deliver here is the full thermal battery system, including all engineering and site services. And the integration into the CSP circuits we see then also on the next page, and while you see here also the picture of the modules being transported from the port of Rotterdam. Here you see a simplified integration diagram where the thermal battery is fully integrated into the thermal oil loop, then providing the full flexibility either by just being charged when the solar plant provides the heat. It can also boost this heat so that additional steam is produced, or it can just produce steam through the thermal battery whenever the sun is not shining. As you see on the right-hand side, it's a steam cycle either then activates a steam turbine to produce electricity, or is going through to process for oil treatment plant. The battery system is quite flexible also within the battery modules itself, where we have a special intelligent mixing system so that we can provide constant charging or discharging temperatures. It can be quite useful, but it also has the very positive effect that we can charge the battery by up to 60% more, because we enhance the temperature difference between the heatcrete and the HTF. So you just see here on the left-hand side, just of course, a constant temperature coming from the solar field. These are not the numbers from Eni, as we are not allowed through an NDA to disclose the exact numbers, but this is a typical application. And then you see that we can either go into a sliding operation mode from the outside temperature or outcoming temperature, or keeping that constant. Likewise, also on discharging, and we can do that either on a 1-step or a multi-step temperature level. That was my short 5 minutes, and if you have questions, just please do not hesitate to contact me. Thank you.
Thank you very much, Hannes, for sticking to the time, and also for this interesting presentation. Now we have, since we needed a bit more time, I had some technical issues, we have around 5 to 10 minutes to discuss several aspects which are certainly of interest. Unfortunately, we find that in the chat function there seem to also be some technical issues, since I don't see there any questions that have arrived. Nevertheless, I would have some questions, and of course I'm happy if each of you can answer to that question by, of course, unmuting yourself. And the question would be, we've seen very individual projects here, and most of you are in very small companies that yes, might have one or two showcases. Are there any approaches or sectors where you find it relatively easy to find the low hanging fruits, or what is your experience in approaching new customers? Because we've heard this more. We have heard earlier by Mr. Taylor that the costs are coming down, and this should be convincing to many industries. But how do we overcome maybe a distrust in the new technology that you're offering?
Maybe I can add a few words to this.
Yes, please.
Yeah, so from Energy Nest side, we have a pretty, let's say, simple system. We do not change phases. We do not have rotating equipment, and we operate with material that is pretty proven. So despite the application that might be a new one, the overall technology is not something very fancy. So that in itself should reassure about the technology readiness. And when we go to retrofit plants, then we normally do have existing boilers, for example, that can be a plan B or backup system to our system. So in that sense, we have an intrinsic fallback position, reducing then the risk.
Okay, thank you. Like simple technologies here to convince new customers and high security. Anyone else that would like to say a word on that? How to approach new customers? Are these personal contacts?
Yes. Sorry. You can also go. Okay, then I take the first match. No, I think it's I see it the same way than Hannes Reuter from Energy Nest did. The approach to the customer and to fascinate them from new storage system, from the possibilities they give to the customer, that's not the hardest part. You have to go. The hardest part starts a little bit later when you speak about, especially if you take the storage as, let's say, stand-alone system, of the integration of the storage to the customer's plant. There are a lot of issues to solve. Sometimes also very costly issues. That could be one thing. The other part is, in some cases, also the regulatory affairs that are covering different applications, and maybe sometimes also subsidiaries. Do you need one? Do you don't want to have one? Did your customer say, okay, it has to be have this ROI within 2 years, or within 4 years, or with the subsidiary in 3 years? Though these are more complex discussions, but they are to solve. And definitely, as you can see, there are a couple of new storage systems, whether it's PSEM, whether it's Energy Nest or Kraftblock, coming to the market. You see the first projects, you're getting a broader acceptance of those systems. But the interesting point in my eyes is that the customer had to get aware of those solutions, had to get aware of the potential of those solutions, and that's the steps we have to take at the moment.
Yes, I agree with Martin. Excuse me. I agree with Martin Schichtel. It's a question of the subsidiaries, of course, and on the other side, these are niche technologies in the moment, and it's sometimes for a lot of people. Also, we have a lot of projects and different projects, and what we need in these new technologies is a common standard which you can fulfill. That you can say, okay, for this application you need such a storage system, and it doesn't matter if you have very high temperatures or if you have phase change materials or what else. But it's the most people don't want to, or a little bit frightened to say, okay, what should we do? It's a new technology and maybe a test. So it's not a test; it's a working technology. But a lot of people say, okay, let's take the old technology. Maybe it's more safe for us, and this is sometimes a problem. So if we have common market, then it will be, of course, easier.
Thank you. If there's anyone else, I've seen we had quite some interest.
I would
go ahead.
Maybe round it up with a final comment from our side. The experience we have made with our customers, which are industrial companies, is that there is basically the opinion in the industry that being sustainable, being CO2 neutral implies additional costs. So everybody is looking for subsidies and incentives, which we all know are in most cases complex systems, the application, and subsidies are basically influencing the market from a political side, which is usually not good. We would see it more that the companies, the industry, should be motivated to reduce their CO2 emissions. So as soon as we put a true value on the emissions or on the CO2 emissions, you know, we all look at a much brighter future. And there is no other way to reduce the global CO2 emissions than also look, or mainly look, at the industrial side, where the majority of the energy is used to produce process heat and steam. So in our opinion, we are on the right way. Yeah, Germany or Europe has started to put a tax on the CO2, but that should happen on a global base. And then I think solar thermal technologies and particular storage technologies will have a bright future.
Okay.
Just one point to add to that. We had different difficulties in different phases of time. Yeah. So first convincing the client, making them understand what solar is capable of doing. Then come the land issue. We make compact layouts. We make containerized BOP. Yeah. We have come across several hurdles, but we come to a point now where people say, hey, you know, industrial clients say, my business is running my business. This is where I want to concentrate. I don't want to bring a big portion of my investment into a new technology. Yeah, I'm ready to go ahead with you, but can you take the risk and then just sell me the heat? Yeah, and it is easier said than done. Now it's the difficult part is to convince you know, pension funds and so on to make them understand what is renewable energy or solar is capable of, and convince them to invest in projects like this where we can sell heat to industries. This is our biggest hurdle, and overcoming this will help us, you know, open a lot more doors.
Thank you. Maybe I've noticed prior to this webinar that there was stunning interest from Mexico. Maybe you, Michael, have also a few issues, and where you see from the studies you are doing, where might be the market niches, where is the strongest interest, and is it really the question of subsidies? Is it the question of reducing CO2 emissions? Do you have any findings on that, on the reasons why do companies invest in solar, heat, and CSP?
Well, I mean, what we're seeing is a development where you know, we're going more from a model where support is required to one that I think takes into greater consideration the fact that the playing field is not level. So there was a very good point by Martin and others that, you know, without a price on CO2 emissions and the health costs of local pollutant emissions that are very significant, actually, potentially, economically more damaging than actually the CO2 emissions. Renewable technologies and solar heat are not competing on a level playing field. So fossil fuels has a very significant financial advantage, and we all pay for that. We don't pay for it in our energy bill, but we pay for that in increased taxes or health costs, increasingly around the world in terms of insurance costs against increasing disasters from climate change. So what we have here is an effort that is, both about developing green growth, meeting the Paris Agreement goals, getting to net zero, whatever it is. But it's also, if we're realistic, we have a public health crisis which renewables can address. And so if you look at the economy as a whole and holistically and what's right for society, then there needs to be the support there to overcome this hurdle that renewable technologies face, right? And so we've seen the policy support for renewable power generation that have driven down the costs, particularly for solar PV and onshore wind. And now it's competitive in many parts of the world, despite the fact it has its hand tied behind its back because fossil fuels still aren't paying. And we don't see the same, it's more challenging. Heat, we're talking about vastly large number of stakeholders. We're talking about different, in terms of government governance, regulation, and all of those factors. It's vastly more difficult to coordinate when we move to the end use sectors, and we haven't seen the policy support that I think is required, and also would very quickly see us bring down costs to a very competitive level. So I think if you look at the problem holistically, you can see the role for renewables. We have the template, right? You invest in driving down costs by scaling up the market and providing certainty for business industry to invest, and the costs will come down. Small modular technologies, low barriers to entry for manufacturing, the costs will come down. But we don't see that. We see these very small markets, with a lot of very innovative products, as we've seen today, and they're not getting the support they need. And so that's the challenge. We need to do that now, not later.
Okay, thank you very much. Yes, for these last words that are very promising. And yeah, let's take the challenge and also take the challenge in our next discussion. I thank you very much for your patience and of course for all these interesting presentations. Unfortunately, we had some technical issues, but I assume that in the next session, which will now continue and which will be moderated by Juliane, it will all go a lot smoother. And I'm handing over to Juliane. Thank you very much. And I would look forward if you would stay to listen to the other very interesting presentations that are still coming up. Thank you very much.
Yeah, thank you, Jan. And welcome to our second session on PV and CSP hybrids and storage, cost-efficient, flexible, renewable energy 24/7. I kindly ask all speakers from the first session to now switch off the camera and leave space on the panel for our new speakers of the second round. And we will start straight away with our keynote speaker, and I'm very happy to introduce to you now Robert Pitzpal. He is director at the Institute of Solar Research of the German Aerospace Center and an internationally recognized expert on concentrated solar power technology. Robert, the floor is yours.
Thank you very much, Juliana. I hope everybody can hear me well. And maybe I need some advice how to move on with the slides. Okay, now I can see it, I think. Yeah, thank you very much and welcome. I'm not sure how the slides are moving. Okay, now it's gone. Okay, the talk is on solar hybrid CSP PV technology. And the question is, of course, why we are thinking about that. And some of the facts that you are probably all aware is that today photovoltaic power can provide very cheap electricity during sunshine hours. So we have achieved costs that are in good solar sites even below 2 cents per kilowatt hour. However, in order to supply energy after sunset, storage solutions are required. And one of them is, of course, the obvious one, a battery storage system. But we all know that this is still relatively expensive, in particular if we look for very long storage hours, for many hours of storage, 5, 6, 10 hours of storage, then these systems become significantly a significant cost factor that is far above the cost of the electricity production. On the other hand, concentrating solar power has typically an integrated thermal energy storage system, and in this combination, and we will talk on that a bit later, storing of energy, shifting of energy is a very efficient and cheap option. And the talk is then on the question, can we somehow benefit from the combination of both, integrating the technology? So start with the PV power plant, and very simple sketch here, the PV system directly connected to the grid allows the lowest levelized cost of electricity, but as I mentioned before, it's actually non-dispatchable. If we have a battery, then we have to consider investment costs for the battery system in the range of 200 to 400 euros per kilowatt hour. And you may keep this number in mind when we later on talk about the cost of on thermal storage. And we are not only paying for the battery investment, but we keep paying also a bit for the efficiency loss in the battery. So putting energy to the battery and back gives us some losses. And in addition, of course, we also pay for the operation and maintenance, in particular for the fact that the lifetime of the battery is actually not the same as the lifetime of the PV module. So on the other hand, you know the concept of a CSP plant. CSP, in this sketch, parabolic trough system, is linked to a thermal energy storage 2-tank system, as it's shown here, with molten salt. The storage, the salt is stored. Sorry, can I go back? Not sure how to do it. Was not moving by myself. Juliana, can you switch this back? Oh.
Yeah, I will hand over. Jan, can you please switch the slide? He's in charge.
Back
okay.
And not forward, please. It's not going back. It's
oh, you want to go back? Okay.
Back, please.
Back.
Back, one slide back.
Yeah, one slide back.
Yes, exactly.
Yeah,
so we are here talking about CSP and the integration of a thermal energy storage. And let me just show you what is actually the benefit or the difference between integrating a storage in between the collector and the energy converter. And this comes if you consider that a solar system provides high temperature heat for about 2,000 full load hours a year to a power plant. And if you add a second part of a solar field that provides to the same time the energy to the storage, the power block can actually produce energy for a longer period of time, or maybe hold the night, 4,000 hours. And this just by adding an investment that is in the range between 20 and 40 euros per kilowatt hour. So a factor 10 lower than the investment in the battery. So if you consider this, then you may understand that the cheapest CSP electricity cost is not at no storage, rather than actually the costs get lower if we integrate a storage and we operate the plant for more hours of the day or of the year. So lowest cost electricity with CSP is actually a system with storage. When we compare this, we see the cost curves, electricity cost per kilowatt hour on the right-hand side, comparing PV and CSP technology. And you see that lowest cost PV system actually is at no storage. And if you add storage, it becomes more expensive. While the lowest cost CSP is actually at a significant storage level. And so the benefit is, the question is here, if we really want to have a system where we have to provide a certain fraction of the power production during the nighttime, or where we have a time of delivery tariff that favor nighttime production, then the combination of both technologies may be combined in a way that we actually get a cheaper system in the combination of these two options. So let's take a look. Next slide. Let me see that. Not moving now. Not sure how this kind of movement is actually performed. Can you somebody shift now the slide? I can't. Yes, thank you. So the combination of both systems may be in a way that on the one hand side, the CSP system is integrated, the PV system provides the electricity, both they provide the electricity to the grid, but in addition to that, we also have an integration that some of the PV electricity may be integrated into the thermal storage. This may be on the first side, maybe counterintuitive, because the efficiency chain, of course, converting electricity to heat and then back to electricity is not very favorable. In the combination, when we consider the cost situation, we will see that there is actually a benefit of this option. So electrical heater is adding energy to the thermal storage in case that there's a surplus energy. So let's take a look to the next slide. Well, a general layout, we can now distinguish between two options. One thing is that, of course, the CSP plant and the PV plant may be connected to the same grid and operated in a way that they match the load. But if we co-locate them, there's an additional benefit. We can access the same grid. We can share the same grid access. We can share the storage options. We can share the O&M team. We can simplify the project development, site preparation, environment and impact studies and other things. And we can also provide more flexible bids to the grid because of the better integration. And all in all, this may lead to an increased profit in the concept of this hybrid system. So hopefully come to the next. Well, let's take a look to the components of such a system. So of course, it's a more complex system. We have a PV system. We have maybe, in addition, a smaller battery storage. This is an option. We have a solar collector. We have an electrical heater system. We have a thermal storage, and we also have a power block. In many cases, it's very beneficial to combine a single axis tracking PV system to the system because they provide a very, let's say, same daily pattern of energy provision compared to a parabolic trough system. And we will see later that this is of a certain benefit here. Let's take a look to the next slide. Sure. Okay. So in this case, that we integrate a parabolic trough and a single axis tracking PV system, there's the chance to put the heating of the molten salt in a serial arrangement. So first of all, we heat the salt with a parabolic trough to a certain temperature, and then we add some temperature by the electrical heater. And of course, it's always important that the energy is provided in the same way during the time of the day. So single axis tracking PV and single axis tracking CSP systems have a similar characteristic so that this actually is matched very well. The benefit is here that the temperature of the parabolic trough that is somehow limited due to the heat transfer fluid, due to the concentration, can be significantly increased, and the power plant can be operated at an elevated temperature with a better efficiency. The other option that is possible is, of course, to connect it in parallel. And I hope the next slide is showing up. Thank you. One back, please. Thank you. In this case, the heat production and the production by the electric heater are put in parallel, and we can independently charge the storage from the battery and from the solar field. And this may be the case because the characteristics, the optical characteristics of a solar tower and of a PV system may be different. The next slide, please. So how can this actually work? When we look to a situation that we want to really provide a base load power, then we have during the daytime energy from the CSP plant and energy from the PV system. And in these cases, typically both systems are designed that for during the nominal time of day, excess energy is available. And this excess energy is actually then provided to the thermal storage, or maybe to the battery storage if there is a smaller battery storage available. And in this combination, energy from the battery storage or from the thermal storage can be used to operate the plant for longer hours after sunset or during the all night and all day. Both fractions of these energy input can be combined in this way. And of course, it's a kind of question of optimization. How large are these contributions of the two systems? It depends very much on the cost, on the efficiency of the system, and so on. So there's no real general answer. And next slide. One additional benefit is when we are talking about the auxiliary consumption coverage. So CSP plants, when they are operated during the day and are not producing electricity, one back please. When they are operated during the day, but they are not producing electricity, they don't have actually the power to operate their auxiliary units. There are pumps and there are heliostats or their collector tracking. And therefore, the combination of the two systems actually gives the chance that even without that the power block is actually running, energy of the auxiliary unit can be provided then by the PV system. So in this combination, we have this real benefit that both systems are running independently and auxiliary power consumption is then covered by the system itself during all the time and not by the grid. And next slide, please. So of course, the question, what is the optimal system? And you may understand there's many degrees of freedom that you can really use. And of course, the optimum always depends then on the specific boundary condition. What is actually the power demand that is needed? What are the price of the components? And many other aspects. But I will show you, let's say, an example here, which is not really representative, but shall show, let's say, what are the factors where you can play with. The one factor that you can play is the relative size of the PV system, and we call it here scaling factor of the PV system. So one scaling is 3 megawatt, and we scale it here by this kind of factor. So 100 would be 300 megawatt of PV. And the same is with the CSP system. So we have a scaling of the thermal power of the CSP system, which we call here rows, the number of collector rows. And each row has here a thermal energy output of 2.7 megawatts. So you can see more rows actually means a larger solar field. And then we have some boundary conditions. The power block is only 110 megawatt, and the power to grid is limited to 100 megawatt. You can see 100 megawatt can be provided around the clock, but the PV capacity is actually in the range of 250 or 240 megawatts. So you can see here the different kinds of optimizations and show the lowest cost of electricity, which is here just from the calculation, a combination of a larger PV of 220 megawatt and 60 megawatt CSP capacity, 60 megawatt equivalent electric power. So you see in this combination, PV system is bigger than CSP, but the optimum actually depends very much on the cost. Very much on the cost assumptions. So it's just an example to show you that you have a lot of flexibility in the scaling of these two different concepts in order to find the best. So next slide, please. Okay, this is just the conclusion. Well, I hope I could show you. We have some
okay.
microphone here.
I think Stephanie Randig tries to get in. We can hear you. Unfortunately, you might switch off the microphone and turn on the camera if it's possible. Thank you.
Okay, just to conclude, I hope that I could show you that these combinations of CSP PV hybrid power plants have really a chance for a low-cost, cheap dispatchable solar electricity supply by optimizing both systems in a way that they perfectly fit to the load curves that you want to do, and you can do this cheaper than with a simple CSP system with storage or with a PV battery system. Of course, the system looks very different depending on how long the storage capacity or the load is actually needed. And of course, the system also depends very much on the subsystem's cost. And as we see a very quick development on these costs, it's very difficult to say this is the perfect optimum solution. It may be a year from now different in the cost situation, and then a different optimum solution will be there. But as you also could see, these kind of optimums are relatively large, so it's not really a problem, and you wouldn't do very big mistakes in this design. On the other hand, this kind of optimization needs, let's say, expertise, and there are software tools under development. I'm sure my colleagues later on will also present their capabilities to optimize this kind of systems and to find the best and most profitable solution for the given boundary conditions. With that, I will close the presentation, and thank you very much for your attention.
Thank you very much, Robert, for the presentation and the great overview of our topic of this afternoon. We actually would like to do a deeper dive now into the economic evaluation of different operating modes of hybrid CSP and PV. Somehow we lost, but the speaker, I'm not quite sure whether we will be able to get him in. Jan, what is the situation? Searching
Hello,
for the speaker.
can you hear me?
Yes, we can hear you. Okay,
But
perfect.
you can't see me anymore, is this right?
Okay, yes, we can't see you, but we can hear you. Perfect. Klaus-Jürgen Riffelmann from the company SPP Schleichbergermann and Partner. The floor is yours.
Thank you, Juliana. So unfortunately, my camera does not work anymore. Okay, so I'm happy to present you the results of a study in which we evaluated different proportions of PV and corresponding operating modes of a hybrid CSP PV plant. And I'm very happy that Robert made his presentation just before me, because he presented most of the motivation, and I can hopefully add some cost figures and show our evaluation, especially for parabolic trough power plant in combination with PV. This is already the next slide. I wanted to show it step by step. Can you go back? And now one click, please. Okay, it seems that the presentation mode does not really work.
Yeah.
It's a PDF, I think.
Yeah, it's a PDF.
Okay. So nevertheless, when I start to explain the reference configuration, which we have evaluated, it is a typical plant in Spain, limited to 50 megawatt nominal power and having a huge storage of, well, finally 15 full load hours. This was an outcome of an optimization in the study. We used our ultimate trough technology as a solar field, and this is a little bit new, we assumed that molten salt will be the heat transfer fluid. By this, the operation temperature of the plant can be increased to more than 500 degrees C, which is very economical or cost effective for the storage. The capacity of the storage, depending on the delta T, is much more cost effective. Such plant will generate in Spain at a typical location about 192 gigawatt hours net per year. On a better location like South Africa, it would generate even close to 50% more. With the reference configuration, we have not integrated any PV plant. And well, about 60% of the electricity generated will be fed to the grid at the daytime, 40% at night. This configuration has levelized cost of electricity of 10 euro cents per kilowatt hour in Spain and 6.2 cents in South Africa. Then with the scenario 1, and Robert mentioned this, we have assumed a small PV plant which is designed just to support the CSP plant and to deliver the own consumption of the plant. With this small PV plant of about 3 megawatt peak AC power, we can increase the output, the net output, by about 6 or 7 gigawatt hours, and the LCOE finally decrease by about 2% for both locations. Next slide, please. Then with the next scenario, the second one, we have reduced the solar field, the parabolic trough field, from 600 to 380,000. And we have doubled the capacity. We have increased the PV plant capacity to 50 megawatt, so that the PV plant can also deliver during the day electricity to the grid, and it replaces finally the solar field of the CSP plant, while the CSP plant only charges the storage during the daytime. And it will produce electricity at night then from the storage. With this configuration, scenario 2, the LCOE decrease in Spain significantly, I would say, by about 10%. In South Africa, it's also going down to 5.9%. Then with scenario 3, no, please go back. Scenario 3 is also on this slide. We have again increased the capacity of the PV plant. We have it doubled to 100 megawatt. And this is what Robert mentioned, that we can additionally charge the storage by means of electrical heaters at the daytime from the PV plant. In this configuration, the PV plant delivers about 1/3 of the electricity by night. The other part is still coming from the CSP plant. And at daytime, the PV plant delivers 160 gigawatt hours in Spain. Yes, and with this configuration, LCOE again decreased a little bit in Spain from 8.8 to 8.6 euro cent per kilowatt hour, while at a good location like South Africa, the LCOE will increase slightly. Now, next slide, please. And this is the final scenario where we have fully replaced the CSP solar field by 200 megawatt AC PV plant, which charges the storage by this e-test concept and delivers in parallel electricity to the grid at daytime. By this, the LCOE finally are higher than for the other configurations, both in Spain and in South Africa. Last slide, please. So I come to the conclusion. In South Africa, as an example for a very good CSP location, the most economic configuration is the one where the PV plant of the nominal, having the nominal power capacity is the most economic one, where the PV plant delivers the electricity at the daytime and the CSP plant at the night via the test system. The e-test concept is less economic at a good location. In Spain, as a mediocre location, it makes sense to increase or to oversize the PV plant and to supply also some electricity by the e-test system at night from PV. Nevertheless, for both locations, it is still correct that if we look only to the LCOE at night, meaning that the plants are only allowed to provide electricity to the grid at night, which might be not a realistic scenario, but it is just mentioned for comparison here. Then the LCOE for the CSP system is much lower than the LCOE for the PV and e-test system. And with that, I like to mention also that the cost assumptions and a lot of other details of the study will be published soon in the proceedings of the last Solar Paces conference. You'll see my contact details here. If you have any questions, I'm happy to answer. Thank you very much.
Thank you, Klaus-Jürgen, for your insights. And for who wasn't in at the beginning, we will share all the slides afterwards so you can study the details afterwards. The title of our event is Heat and Power Production, but you can do something else. You can do hydrogen production as well with CSP and PV power plants. And I'm happy to welcome Oliver Bautzen from TSK Flaxol to share his insights. So the floor is yours, Oliver.
Thank you, Juliana. Hello, everybody in this web session. I'm going to speak about integrated CSP PV hybrid systems, what we call briefly ICPH. And in particular, I want to focus its fit to the green energy for hydrogen industry. We have, before I start, I want to emphasize that we always distinguish the integrated systems as we have developed it as TSK Flaxol, for instance, for the application in Morocco, from the simply co-located plants, because we believe and we can show that those integrated systems are more efficient and more advantageous in terms of LCOE. The next slide, please. So we have heard already by Robert and also by Klaus-Jürgen how such an integrated system works. So I just want to refer to two main aspects. We have here the two inputs of energy from the PV field and from the parabolic trough field. And we connect these two energy sources here over an electrical heater. And this integration has mainly two effects. The first effect is we increase the delta T between the cold and the hot salt. This means that we can increase the storage capacity. And second, due to the increase of the temperature levels, we improve the efficiency of the water steam cycle. So we have two major effects, as they have been explained already before. And with that, we have a system which is very perfect for hydrogen production. And let's go into some aspects of that on the next slide. Thank you. So first, it is important to get one thing clear. If we go for hydrogen production, particularly green hydrogen production, we have to make sure that we allocate and connect each hydrogen generation facility with its own allocated green energy source. Otherwise, we endanger the energy transition because we steal from the system green energy. And we have the risk that the hydrogen production is not supplied with green, but with black, gray, or whatever energy. This said, the ICPH power plant concept can be designed in such a way that we can achieve easily more than 8,000 operating hours. That is not falsely at 100% load, but bigger than 50–70% load. With that, we have a very strong usage of the invested capital of the electrolyzers and of the power plant, of course. And this leads to process and production security, not only in the power plant part, but also in the operation of the electrolyzers and any subsequent downstream process such as ammonia or methanol. Another interesting advantage of CSP systems is that we can, in addition to power generation, electrical power generation, we can make use of the thermal heat of the system. We have talked largely in the first session about process heat, and we can here deliver even combined heat and power. Then we can provide grid services, not only the frequency stability. With such a system, with the ICPH system, it is also theoretically possible to participate in the reserve market. Another advantage inherent to CSP technologies or CSP-based power plants is a strong local content we can create, what is important for the socio-economic development of the region and the country where this technology is placed. And if we talk about green and sustainable production of energy and hydrogen, it is of the importance to have systems with a long lifetime so that the investment can pay back well, that we use non-critical materials with a non-critical supply chain, and that the recyclability is given. And then, last but not least, we have a system which with very attractive cost in terms of energy and of heat. And I would be even more aggressive than Klaus-Jürgen before. We are sure that we, within short, can target cost below 6, going down to 4 euro cent. Of course, depending on the site and the context of the project and the final design of the power plant. But this is the target of what we can do. And let's say 4 to 6 euro cent baseload solar power is incredibly good. Next slide, please. Just to give you an outlook on how ICPH concept can be used in the hydrogen technology. We have drafted here an overview. Can I operate the mouse? Can you see my mouse?
Yes.
Okay.
We do.
We have here the starting of the process with water injection going into the electrolyzers, producing hydrogen, which is sent to the methanol plant. We have here from a cement production, the extraction carbon capture system of the CO2, which is also sent to the methanol plant, and then we can produce a green methanol. The interesting thing here is that the CSP PV hybrid system is integrated into the entire concept of this value chain, providing green energy, in terms of electricity, green electricity, and green heat to all of these systems. I know that is in 5 minutes a lot of information, but I'd be happy to answer later on questions if there come up some. Thank you for your attention.
Yeah, thank you, Oliver, for your presentation. And I will directly hand over to Stefanie Randig from Siemens Energy, and she will talk about the performance enhancement by hybridization. The floor is yours, Stefanie. We cannot hear you now. Could you're still mute?
No, I hope you can hear me now.
Yes, perfect.
Okay. So thank you, Juliane, for your introduction. So in addition to the presentation of Oliver Bautzon regarding the ICPH, I want to inform you about advantages by combining the CSP and PV in a hybrid plant. So please, next slide. Please, okay. With our broad steam turbine portfolio, we offer turbines for different types of CSP plants. So in addition, we support the steam and water cycle optimization for our customers and help them to find the best possible plant design. So please, next slide. And based on our experiences in the CSP market, we want to share with you our ideas regarding the integrated CSP PV hybrid concept. With the new concept of hybridization, an enhancement in performance can be achieved. So in an ICPH plant, the molten salt is heated up in 2 steps. In the first step, the cold salt tank is heated by parabolic trough to a temperature level of 390 degrees Celsius. And in a second step, a photovoltaic system and electric heaters are used to further heat the salt. And with this hybridization, a temperature level of 560 degrees can be reached. The increased temperature in the molten salt cycle has a significant impact on the efficiency of the water steam cycle. Please, next slide. And in order to calculate the impact on the water steam cycle, our thermodynamic experts compared 3 plant designs. The first design is the classic parabolic trough plant design. The second design concerns the current state-of-the-art design of an ICPH plant. And the third design on the right side is an optimized design concept. Here we call it future concept. Please, next slide. And let's have now a deeper look on key parameters of the water steam cycle. All 3 designs are characterized by an output of 190 megawatt. You can find the main differences in the steam inlet parameters and further parameters. As a result, the water steam cycle efficiency is increased by 6.3% in the ICPH plant compared to the classic design. And the efficiency could be further increased by another 1.4% according to our calculations. Please, next slide. So let's also have a look on the salt cycle. I already told you in the ICPH plant, the salt in the hot tank is heated up in 2 steps. In step 1 by parabolic trough and in step 2 by a photovoltaic system and electrical heaters. In the classical design, we have a usable temperature difference of only 117 Kelvin. And in the ICPH design, we have instead a usable temperature difference of 287 Kelvin. And that's an obvious advantage. Comparing the classic PT plant and the ICPH design, we see a significant decrease of more than 60% in the needed salt flow and the salt tank design. And in addition to, we have with our calculation shown that there is further optimization potential. So please, next slide. Now I want to summarize the advantages of the ICPH plant design. Due to the hybridization, we see a significantly reduced salt flow and salt tank sizes. Because of a higher water steam cycle efficiency, the total amount of needed solar energy is reduced as well. And in total, a reduction of the plant LCOE can be achieved. The future concept shows further optimization potential. Yeah, now I have already reached the end of my presentation. Thank you for your attention. And if you have further questions, please don't hesitate to contact us.
Yeah, thank you, Stephanie, for the brevity and for all the details. I think one needs to take a closer look, and we're happy to share all the presentations later on. We will now move to a startup company, and I'm happy to present to you Caspar von Moy from the company Heliovis, and he's just asking dust, hot air. The floor is yours.
Thank you very much. Good afternoon, ladies and gentlemen. I had just noticed that this whole second section was very technical, and it was all about the integration of CSP and PV and the advantages and benefits of that. My presentation, or our company, is really about applications of CSP, so this slightly provocative title might be really fitting here. And I hope to be able to show you in this presentation that indeed what we do is more than just hot air. Now, let me see if I can click. No, I can't. So I'll ask you, please click once for me. Okay, so what we've developed is a new inflatable solar collector, which is made of 3 industry-proven plastic films. And the collector is formed through a pressure difference between an upper chamber and a lower chamber, which is separated by a mirror film. Is this going to work? No. Can you click for me? Whoa, whatever happened there? Help.
Yeah, I think this is because 2 of you are moving it. So maybe. Okay. So Jan, you might.
I wonder. There we go. Okay. Could you click for me? Thank you. It works in the same. Whoa, okay. Enough. It works in the same way as a parabolic trough. So sunlight enters the system through our transparent film up here, is reflected off the mirror film and concentrated onto a receiver. The dimension of the system is large. The length is 220 meters, so that's the equivalent of 2 football pitches, and the diameter is 9 meters. Output parameters, we have 0.9 megawatts of thermal power per heliotube in a temperature range of 90 to 550 degrees for up to 24 hours with appropriate storage technology. Now, the system has a number of specific features, and I'd like to focus on 2. One is the entire technology is designed for harsh desert conditions and maximum durability. And the other, due to the special features of the design and the materials used, we have 50% lower capex and 20% lower opex versus the standard parabolic trough technology, which leads to a cost of thermal energy, which is really very suited for industrial process heat and water desalination. And I'll say a little bit more about that later on. Click, please. The first full-scale project that we implemented was in 2017 in Spain. It was funded by the EU Horizon 2020 program and is very well documented. And what you see here is one of our heliotubes in its full length, 220 meters, with a support system around it, the wind fence. We have replaced some of the central elements with PV modules. This has worked extremely well, and we now offer all of our plants with a sort of integrated approach. Here's a small pressurized hot water tank as a heat storage, and with this, we deliver, if you want, industrial process heat to our customer, who is an agricultural producer. Now, what is of course a little unusual about this is that our standard solar field would be 30, 50, or 100 of our heliotubes, and here it's only 1. Now, a really interesting market, click please, in which we're experiencing a lot of traction next to the industrial process heat market, is this market for water desalination. As I'm sure you're all aware, water scarcity is already an issue today, and it's becoming more pressing every year. It is being addressed, of course, with desalination plants, and the dominant technology with over 95% market share is reverse osmosis. This operates at high pressures, therefore needs to run 24 hours a day, and therefore requires constant energy supply. And since they run on electricity, they need baseload electricity. Often, therefore, large plants are situated directly next to power plants, as in this case, leading to a heavy carbon footprint. The second issue that this technology has is that the rate of water recovery on global average is about 40%, meaning that for every 100 liters of salt water, you produce 40 liters of fresh water. Oops, could you go back, please? Thank you. And 60 liters of concentrated salt solution, which is usually pumped back into the ocean close to the coast, where it leads to damage. So if we're going to tackle the global water problem with this technology, it's going to come at a heavy ecological price. And there are alternatives, and we can provide one of them together with a technology partner who has a desalination technology that runs primarily on heat and does not use any high pressures. And together we can deliver water at competitive price levels with very little or even no brine, so none of this salt solution. And the system is self-sufficient in energy and therefore CO2 neutral, with the added benefit that we can work off-grid, which in many of our target markets with their infrastructure challenges is a great benefit. If you could click to the next slide, please. We've developed a system based on standard units, which we can use multiples of and therefore scale the system. Each unit produces 6,000 cubic meters of fresh water per day, and we achieve recovery rates of up to 96%, the remaining 4% being basically wet salt. The fresh water prices we can offer with this are between 70 US cents to $2 per cubic meter, depending on the specifics of the project. And this is ideal for, say, large agricultural companies, for industrial companies, or for local communities. And the ideal applications or the ideal settings are everywhere where there are ecological sensitivities. So either coastal regions, inland desalination is a big, big topic, because there, if you have large quantities of brine, you don't know what to do with them. And here, if you have either industrial wastewater or mine wastewater or underground salty water, we can use this. And of course, anywhere with poor grid connectivity. We're currently working on our first projects, and I hope to be able to introduce these to you next year. Last click, please. With that, thank you very much. And if you're interested in our technology, we would love to hear from you. Thank you.
Yeah, thank you, Caspar, and also for being right in time. And we will now have a closer look to storage systems. And I'm happy to leave the floor now to Martin Schlecht from the company Suntrace, and he will tell us more about the benefits of energy storage systems for the energy transition. Martin, your 5 minutes
Hello,
start
good
now.
afternoon. Can you hear me well?
Yes.
We hear you well, yes.
Okay, thanks. I decided not to give a closer look, but more a distant look, because everybody has been very close in the previous presentation. So we see a lot of pilots and examples and showcases for solar thermal heat production in different applications. We discussed the PV and CSP hybrid in length, which I was in the early stage involved with Mazen tendering out the MEDEL1 project. That has maybe inspired a couple of the presenters that were presenting before me. So I thought that I wouldn't go for the PV CSP hybrid with this presentation, but rather look more generally at the storage requirements at least, and also looking forward, what is it for the energy transition? Can you go forward to the next slide, please? I'm mainly putting up a couple of factors that I have taken from SMAP report and from Energy Watch Group and LUT University from Lappenrad in Finland. They produced a report how a 100% renewables by 2050 could be feasible. And their method and everything that can be discussed for sure. There is not too much CSP in it, but I'm still finding it very valuable in its general message. And that implies in particularly that there is a very strong increase in electricity generation, not only to supply energy to the electricity sector, but also to supply electricity to the transport sector and to the heat sector. But there's also another element that is where the heat is used also to generate electricity. And that's an interesting part. And the main message is that there is energy storage, be it electrical, chemical, or solar, thermal, or heat, will play a very key role to integrate the renewables going for 100% renewables future. And they also come to a message where they say that it's possible to do it based on existing technologies. Basically, you don't need to find a new invention that's not existing to get this done. It can be done by applying the systems that we already have. Please go to the next slide. For example, the study concludes that going for the 2050 100% renewables, there will be maybe a 17% share of the renewable energy coming from an electric storage. And that's from an energy storage to converted to electricity, let's call it like this. And they say that currently that is mainly maybe batteries and similar things that are just getting electricity in and putting electricity out. But going forward and going into the night and going across the night and having some 24/7 applications, maybe the battery storage is also not the full scale. And there's other systems as well that can provide thermal energy and then convert it to heat, something that is, for example, proposed in the CSP PV hybrids in a large scale. But they, of course, they're looking at Europe and they're looking a lot more into the small scale. But I found it intriguing to see that projected development curve over the next years and to see where we are in terms of storage capacity today and how much it would need to scale up going for the 2050. It also involves what they say a significant amount of gas storage that is considering green gas created from hydrogen, green hydrogen, for example, that could use provide as a seasonal storage in particularly for Europe. But I don't want to emphasize too much on this. The other part is, of course, it's not only about electricity, it's also about heat. And we have seen a lot of examples in the different presentations. Maybe you can switch to the next slide. That shows that for the heat generation, you have mainly a thermal energy storage that you would be using. Of course, you can generate thermal heat from electricity, but you can also generate it from other sources like CSP, for example. And the energy storage for heat, the thermal energy storage, will cover a large part of the heat storage output in the years to come. Power to gas, green gas will also contribute some part of it. But in particular, when it comes to quitting the fossil heat generation, that will definitely increase also the requirement for heat from a thermal energy storage. And you can see that the share where electricity is converted to thermal heat is not as much from an electricity storage as if you had a thermal energy storage in the first place. Please go to the next slide. They also say that effectively that can be done over the next 50, or no, it's only 30 years left, that it can be done while reducing the cost, both the cost for electricity, the levelized cost of electricity, LCOE, but also the levelized cost of heat. And that is implying the use of storage. So a lot of discussion that we have today is about energy storage is too expensive, there is no business case, and it's a lot of issues. But when we want to go to the 100% renewable, we need to have business cases for storage, and we need to have a scaling of the different applications. And I found that intriguing to understand that for going for the energy transition in heat and even going for the energy transition in electricity, we need also thermal energy storage and not electricity storage. And as it can be seen here as well, it's not about either or, it's both. it's like previous, we had a lot of discussion about either PV or CSP. Who is the winner of the competition on solar electricity? There is no winner in the sense that both will have some contribution, and one is maybe bigger and one is smaller, but you cannot leave out one of them. And the same is for the storage. And so I wanted to bring this just up as a food for thought, and maybe take the heads a little bit out of the little details of the individual projects and all the digital figures that were presented, and give a heads up and say every one of us, of these presenters and of the crowd, is going towards the right direction. What we, I think, as a whole industry need to work on is to remove barriers, to get a level playing field for those applications, find the funding mechanisms and payment mechanisms that are making it work to go into the large scale, that allow a ramp up of manufacturing and allow a ramp up of all the implementation of storage. So that's just my part, not delivering a system in the industry, but an opinion and the technical advice from Suntrace. Thanks very much.
Thank you, Martin, for the opinion and for the broader view on storage. And yeah, with that, we move now again to a more detailed view on storage systems. And we will talk now about steel storage systems, high temperature steel storage. And I'm happy to introduce to you Constanze Adolf from Luminium. The floor is yours.
Hello, everybody. Well, I've got the challenging task now to keep you alive until we get to the discussion round. Martin, thank you so much. I mean, there is nothing to add from my side on this, because I'm so convinced that the challenge that is ahead, and I think this afternoon showed very precisely that we have all the technologies. The puzzle is there. It's just the question now how to set all the pieces together in order to make 100% renewables possible. And I think there really, it's not about a competition, it's really to try to show how complementary all those technologies are and how they are in a way needed.
Constanze, we can't hear you anymore.
Can you hear me now?
Yes, yeah, it works.
Okay, so I hope that you heard my first part, that I really thank you all for your great presentations.
We did that, yeah.
So the Luminium technology, in a way, is driven by the idea that we need very simple solutions to the complexity that we've seen before. And so the basic idea is that we would charge electricity. However, our storage system is also able to kind of get heat waste, steam, or solar thermal energy and to store it. So the basic idea to kind of charge electricity is obviously to avoid curtailment and to stabilize our grids, as well as to really create added value at site. And then we provide heat and steam to different applications. One, and something that we heard already, is district heating. So everything which is around existing district heating systems, meaning temperatures something between 90 and 120 degrees. But then also industries with temperature up to 650 degrees. Important to that for us is also the idea to provide brownfield projects, and we heard that before as well, to really complement existing technologies, because as I always say, it's more about an evolution than a revolution of all the different technologies. Next slide, please. And so here you can see our very small district station here in Berlin. It has got only a capacity of 2.4 megawatt hours. So it's a rather small system that supplies hot water, but also heating for 400 apartments. And this was, one of our first really commercial projects. Next slide, please. But I would love to take you further to one of the regions in Germany, which is Schleswig-Holstein, where you've got all the windmills, and so a huge kind of level of curtailment. Here we will build, this is a greenfield project, we will about to plan a 20 megawatt hours storage system for Europe's biggest organic process plant for vegetables. So it's a freezing plant with around a production capacity of 240 tons per day. And what I like here is also, Martin, something that you mentioned, it's about this kind of bringing systems together to have, on the one hand, organic farming, but on the other hand, renewables. And sometimes they seem to compete about soil, about land and all the stuff. And here you really can see that this all can go together. Next slide, please. But I mean, it's a little bit later in the afternoon, so let's go to whiskey. So this is a very nice project and one feasibility study that we just kind of finalized last week for the Orkney Islands in Scotland. So you learn a lot about whiskey, and actually I didn't knew that whiskey is so energy intense, so 10 times more than gin and other kind of alcohol drinks. So here we can use our storage system obviously to provide the heat for the distillery, but also to show that if you are in very rural areas with a very low level of infrastructure, that you can get this kind of independent energy supply 24/7 with volatile electricity supply. Next slide, please. So where do we want to go? This is where we want to go. So we've got some big feasibility studies running now for really replacing really big plants. But I think the most important thing is, again, to show that with different systems, we can match different technologies. And the biggest thing about this, and this is also maybe one of the next kind of discussion points again, I think the technologies are there. It seems that everything is running. We know about the difficult regulatory framework, but it's really a big kind of opportunity, but also challenge to go into society and to show them that this is all possible. And I hope that all together we can do this in the future. Thank you so much.
Thank you, Constanze, also for the perfect timing here. And thank you to all speakers, because we are now about to finish all the presentations and want to continue with the discussion. We have 15 to 20 minutes now to go a bit deeper into some details. Unfortunately, our chat doesn't work, but I'm sure all the speakers will be happy to answer questions individually if you write to them. I have a question now. Constanze said it. We've seen a lot of technologies here, proven technologies, and we have seen that they are also competitive in the sense of costs. So what is it? What are the main barriers now to prevent the solar thermal sector and the storage sector from boosting now? Who wants to start? Martin, maybe.
I would leave the floor to somebody else first. Thanks.
The main barriers.
If you may allow, I think one of the major hurdles is that for major projects deploying such technologies as ICPH or similar, we need highly sophisticated and financially strong IPPs, and we need to educate them and others about this technology, because it is still new for them, and it is a hurdle to go for huge investments with kind of new technology approaches. And therefore, I think what we have seen, for instance, in Morocco is a good exemplar on how to proceed and how to set correct frame conditions and how to catalyze large-scale projects of deploying new technologies. And in Morocco, we can see big success there. Yeah, I think education and attracting the big players is one aspect, and of course also for medium and small scale projects, it is the biggest hurdle is certainly the unknown of the technology, and we have all to work jointly on the fact to bring this knowledge to the market.
Mm-hmm. Someone wants to add something. Was that? Yeah, Martin?
Now I'm ready to respond. Sorry about that. I think the biggest part is that everyone is used to tender. If it's an IPP for a PPA, like in many countries outside of Europe, and even inside, all the schemes for auctions and tenders are for single technologies. And usually they don't even allow a blended technology if it's PV and wind and battery, or if it is PV and CSP. Maybe now it comes that it could be wind and battery, or it could be PV and battery in large scale projects in different markets. But no one would allow a CSP PV hybrid to compete when they tender out a PV and battery project. So there is a limitation in the perception of the authorities that are actually wanting to have a low cost and reliable supply of electricity also into the night. And so I think there is a barrier, not by the price and by subsidies that it needs, because it's becoming very competitive now with what Oliver said, 4 to 6 cents. It's undercutting the cost of coal in certain countries. And of course, it's undercutting other fossil energy generation. So there is definitely a perspective, but it's not allowed. And they don't even think about it, because the perception of CSP is like it's hugely expensive, and no one is aware that it could be in a competitive range. And unfortunately, there are just few projects that could demonstrate this competitiveness on the planet. And then also another point is, from looking at CSP, everybody will see that battery prices are falling, and then they will say, oh, there is no future for the thermal storage as well, because battery storage will pick up. But if you look at the different scaling, it's also quite interesting. If you scale linear, the battery storage for longer hours, you have to scale the PV and the battery in a linear manner. So it's like 1 more hour, you double the plant. 10 more hours, you multiply the whole PV and battery by 10 times, basically. If you go for a 10 times longer CSP instead of 1 hour for 10 hours, then you scale the solar field, but the tank just goes a little bit higher, but you don't put 10 turbines and 10 power plants, you just have 1, and you have a bigger storage. And so in this case, the benefit for the CSP and the thermal energy storage definitely comes in the longer operating hours from the storage. So there it's less competitive for 1 to 3, maybe 4 hours. And we see that the gap where the CSP really becomes beneficial is when it goes closer to baseload. And that will most likely remain for the next years. And with the efforts from the industry, it will go down in parallel to this battery cost that also will go down. Thanks.
Yeah, thank you for, yeah.
Maybe one point for me, I think something that is also missing is a kind of front runner. I mean, coming back to batteries, we don't need to name anybody, but we have, I think, 1 or 2 persons in our head, which is not really true for systems that were, in my opinion, maybe this is wrong, but in my perception, that represented today. So one of the clients that we have, and this is the agricultural project, that is really something very beneficial for us, because we have a client who says, I want to try it. And this is a real kind of, obviously for him it's a risk, because we've never had such a big project really built, and meaning that you all know what it means. And so that means you need also people with courage, and you need people that really want to show that this is a kind of front runner position that they want to have. And I think we need to encourage this as well. And then obviously in the second, or the most important thing, as you said, is the economic benefits to it. And I think this is also a political question. If you calculate the cost of climate change in the future, and if you then just balance it out against the carbon price, it's definitely not enough. We know that a ton of carbon costs around 180 euros. So I think there, and this is something that is definitely frustrating for me, is like, until when do we need to wait, and which catastrophe do we need until politics will wake up and really get the prices and the market right on this?
May I add maybe additional perspective on this? This is of course now from a relatively young company and small project point of view, and not the same as maybe Mr. Bautzon has in your large projects. But one thing that was already mentioned in the last discussion group, and which I think is very valuable, and we found this to be very helpful as well, is that of course our customers, they are not keen to have large capex expenses for new technology which they feel insecure about. Even if it's technology which may be proven in other settings, for them it's new, and therefore it's difficult and it carries risk. And any kind of financing solution that we as technology providers can provide with that, any kind of model where we have offtake agreements for the heat, of course that will always need a backup solution, but usually there are already some kind of I don't know, a gas burner or something in place, so there is a backup solution. But if you can then provide to a potential customer a fully funded solution where all he needs is to accept your heat into his system, that lowers the barrier. And then if sequentially there are more and more of these projects, then the prejudice that might exist currently in the minds of many of our customers will become less, because the competition has it, so they want to have it too. So I think what we can really do as companies is try to find smart funding solutions, and there are some around, to help our customers overcome these barriers.
Mm-hmm. Okay. Was there a sign? No, it was not the sign, Martin. No, it was not. Okay, yeah, thank you for that. I think talking about markets, or where we can start, I think there are some markets who start to move, or where the governments look closer to CSP. Can you tell us where are the markets, who shows interest, and where is best conditions in sense of policy framework? Who wants to start? Nobody? Aren't there markets, or is it difficult?
I mean, the big CSP and PV that we have discussed, it looks pretty much for the Arab region, and maybe China, and then again maybe for green hydrogen for Northern Africa. That's focusing on electricity. I find it quite intriguing that here are so many project examples that show thermal heat and process heat at different levels. Produce 50 or 70 degrees from concentrated solar maybe is not too much efficient, and maybe you go for flat plate. But when you go beyond 150 degrees, there is no such other technology than CSP. You either use electricity for heating, or you can use solar thermal. And there was some, at least some indication from Klaus Riffelmann that when you go to a larger, to a certain point, that then the CSP could be a benefit, a cost benefit to the client, and not only put it PV or buy the electricity from the grid for heating, just to avoid your CO2 emissions. The only thing with heat is you cannot transport it across long distances. So you have to have a consumer that has some space to put a solar thermal system next to him, and that is willing to go for the technological and financial integration, or have someone that is funding him as an off-taker, an IPP, or I don't know how it's called, a thermal power plant, an independent thermal power plant, to send him the heat from renewables across the fence and sell it under an energy supply contract or something like this. So it's much more cumbersome for the heat to find the clients that are trusting the reliability of the supply and then implement systems. It is very tailor-made. It's very on a personal level on each of the factories or the consumers, even if it's just a bakery or a very small user. But it has to be implemented in a huge scale to achieve the transition goals, and that's the real challenge. You have tailor-made solutions in the kilowatt or small megawatt range, and you still need to get to the point where these are being implemented. And I think that's the toughest challenge currently.
Mm-hmm. Thank you. Robert, you wanted to say something?
Yeah, maybe everybody's wondering why we have so much difficulties to tell where are the markets, and that's actually the difficulty that the markets right now are really actually very small. We have some particular chances in the countries that have been mentioned before, but I'm quite optimistic, because when we look to the situation that the world is committed to go to decarbonization, and I see all the trends all around the world, we go to decarbonization, no question about it, then it's only a matter of time that people will understand that they need each and every technology that has kind of benefits here. We have the benefits there, and there will become a need, either pushed by CO2 emission taxes or by other regulations, because people will understand that with the approaches that they are following right now, they cannot achieve the goal. They cannot achieve the goal, and they will have to look for further options. And we are one of the low-hanging fruits, maybe not yet well recognized by everybody, but the technology is one of the low-hanging fruits that can provide a lot of things that the other low-cost technologies that we have today, wind and PV in particular, cannot. And therefore, maybe the market for today is not easy to spell, but the market for tomorrow will come up, and I'm very sure about that.
Okay, so to foster, to create the market for tomorrow, to make tomorrow a bit more now,
We have somehow lost Juliane. Is this?
Seems so.
So maybe we can anticipate her question somehow, which would be most likely how to shape what is needed in order to shape the markets for tomorrow. Maybe we can discuss that. I think what is very obvious is to have a clear understanding and a clear chances to show that this technology is running, that there are cost reductions going down, like we have shown today in the study that has been presented by IRENA, and that there are real beneficial opportunities. And we have opportunities, but not so many, and there are not too many, let's say, or there are limited countries that have already committed to go into that direction. So there are more options available. So we need to work on expansion and the convincing of future markets. And I would say not only in the direction of, let's say, policymakers, of course, that is needed, but also in the connection of industrial partnerships. So if we are considering now large-scale PV and CSP industry, and there is a big PV industry already. It's much bigger than the CSP industry is, and we have to find the right partners and the right connections, maybe also with thermal process heat and other things. There are companies in the range available, and we need to have partnerships to have a bigger, let's say, consortia, bigger impact in these markets, and push in the right moment with the right option and the right technology, and also push for the situation that that tenders are done in a way that they're open enough to give our technology also a chance. Juliana is back.
Thank you so much. Yeah, thank you so much for leading, continuing the discussion.
I'm back. Yeah, I had to change computer. In the last minutes, I got lost. Okay, so someone wants to.
We have anticipated your question, and maybe there are more people who wanted to contribute. I just see Valeska nodding, so go ahead.
No, I'm just delighted how you continued and led the discussion and answered some very relevant questions. I'm actually a representative of the BWS, the German Energy Storage Systems Association, so I would like to leave the floor to the different industry representatives to continue the discussion. But thank you.
Yeah, thank you, Valeska, for your help. Indeed, we have 5 minutes left on the clock. Something urgent to say in this round? If not, I would like to close it and say thank you very much to all the speakers. I greatly appreciate your participation and your very informative and inspiring contributions. I think we will continue to discuss the topics in other rounds. And just let me say a few remarks on today to close our seminar here. What did we hear? We hear solar thermal energy, whether concentrated or not, together with thermal energy storage, can provide emission-free process heat for the industry, and there is a great potential to make it an important contribution to the decarbonization of the industry. We also saw that integrated CSP and PV hybrid systems with thermal energy storage can provide flexible renewable energy 24/7, day and night. And it has been demonstrated now that solar energy with thermal storage offers competitive solutions, and also regarding the costs. And however, there is still a great potential to cost reduction. And yeah, today we covered a wide range of solutions and best practices, and we've seen a lot of proven technologies and innovative applications and projects, and we got to know companies who offer them. And at this stage, I want to repeat something that I heard several times also during the Berlin Energy Transition Dialogue. This decade is key to bring the energy transition on the right track. And we need to take decisions, and we need to act soon. And I hope all of you, the audience, today you got some inspiration to do so. Thank you so much to all of you for joining us today. Let's stay connected. Thank you.
Bye-bye.
Bye-bye.
Bye-bye. Thank you for organizing, Juliana. That was a very good event. Thanks.
Absolutely. Thank you so much for organizing.
Thank you. Bye-bye.
Bye-bye.
Bye-bye. Bye. Also, Jan has to say goodbye. Bye-bye. In the back.